Hi Spring fans, welcome to another installment of Spring Tips. You know, Spring Boot 3 is just around the corner. Not too far from now, in fact. It'll be here before the end of the year, 2022, and it is packed to the gills with amazing new opportunities. Chief among them is the AOT support. This new stuff is new, and it may very well change, but I wanted to talk to you about it now while we are ramping up to the big day, the big release. Some stuff doesn't quite work yet. And I'm not recording this video as though I won't ever have to re-record or change parts of it. I know I will. You should know that you might have to as well. That said, there's a lot of stuff that's already pretty firm and pretty solid at this point, and it's worth taking a look because there's some big implications for this new introduction into the Spring universe. Obviously, we need to have some code, right? This wouldn't be a Spring Tips video without code, so let's get right into that first and foremost. All right, let's get right into it. We'll go to start.spring.io, and we're going to build a brand new application using 3.0 M5. This is Spring Boot 3.0. This is the latest milestone just released as of this recording. Obviously, feel free to use anything later than this when you do your run through this. I expect that this will have a long tail, so feel free to do that. We're just going to call this example project AOT. We're going to use Java 17 for a number of reasons, not least of which is that coincides to the latest stable version of GraalVM as well. Java 17 is the baseline required version for Spring Framework 6 and Spring Boot 3. It may seem quite an aggressive move right now, but consider that by the time Spring Boot 3.0 is GA, we'll already have Java 19. Java 17 will already have been more than a year old by this point. And the latest version of Java could be, given another 5-year window as we had between Spring Framework 5 and Spring Framework 6, it could be another 5 years before Spring Framework 7 is released. And if we get 2 new versions of Java every single year, well, then that's 10 more versions. We could be well at Java 29 by the time Spring Framework 7 drops, maybe even later. Who knows? So by that point, the idea that you can be using Java 29 and Java 17 and still be supported in the same generation of Spring is going to seem a little insane. But that's the kind of a long tail that Spring endeavors to support. Now, for our example, we're going to use Lombok, we'll use H2, we'll use Tomcat and Spring MVC, and that's it. There's nothing special we need to do to enable the ahead of time GraalVM support. That's just baked into Spring Framework 6 and Spring Boot 3. So we'll hit generate, and that'll give us a zip file that we can open up in our IDE. And we're going to need to set up an instance of GraalVM, right? And you can do that as well. You can use tools like SDK man. So you can say SDK install Java, and then it's 22.2R17 GRL, I think. So let's see if that works. Yeah, it's already installed. That's what I've got. And so Java version. And you can see it says OpenJDK 17. Remember, GraalVM is basically just a drop-in replacement for OpenJDK. And we have this build and this runtime environment specified here, stipulating that this is the GraalVM Community Edition. All of this is open source. You can use it. There is a GraalVM EE Enterprise Edition, I think, and that version's amazing. It's got even more features that make GraalVM even more compelling. And I truly hope that Oracle and the people working on GraalVM make a lot of money. So if you have any interest in that, please do check it out. Probably a use case there for you. I'm a big believer in supporting the people that make production work. So good stuff. All right, so we have a brand new Spring Boot project. If you look at the pom.xml and you come at this from the perspective of, let's say, somebody who's used Spring Boot 2.x and Spring Native, you will notice that a few things are missing. Obviously, we have the snapshot and milestone Maven repositories, and that's just for the fact that we're not using a GA, generally available released code. But otherwise, it's just a stock standard Spring Boot app. Look, there's no Maven plugin here for native, there's no AOT plugin, there's no extra dependencies on the class path. We're just back to a stripped down, bare bones Spring Boot application. And we've got our H2 dependency, we've got Tomcat. I also want Spring Data JDBC, maybe we'll do some basic ORM, so we'll add that in as well. So there we go. Just a regular stock standard Spring Boot application. Let's just rebuild. and we'll get a simple compile going here. Maven d skip tests p native clean package. All right. Now before I do that, let's just build out the application. We're going to call this AOT application. I'll create a new package here. I'm going to call this basics, yeah? And we'll have a new configuration here, basics configuration. And it's just a Spring Boot class, Spring configuration class. We'll register a listener of type application ready event. And we're just going to call this basics application listener. Okay, and when the application starts up, we'll listen for this event, application ready event, and we're going to inject a pointer to something called a repository. So I'll define that here. Customer repository extends CRUD repository. This will manage entities of type customer whose primary key is of type integer. And this in turn implies an entity of type customer, integer string name. Okay, so good. And I'll need that here. So customer repository. Good. Now let's just write some records to the database, okay? Save all, stream.of. Let's just get some names, A, B, C, dot map, name, new customer, null for the ID, name, and then to list, okay? So I'm just saving it all, and then for each one that comes out, system out print line. All right. Okay, there we go. Good. There's this. There we are. Okay, and with that, we're going to write some data and we'll see it logged out to the command line, to the console when the application starts up. So let's just run this on the JRE. Okay, it's complaining because we don't have a database table. Okay, so let's go here, source main resources, create a file called schema.sql, create table customer, ID serial primary key, name varchar 255 not null. I forgot to annotate this with @ID. I'll restart. There we have it. We have our application. It starts up. It's got 3 records in the database. It starts up in 0.885 seconds. That's fine, but I'm here for AOT. So let's kick off one of those builds. All right, the application is finished compiling. If we go to the target directory, we have our so-called fat jar, but we also have the AOT binary. Let's go ahead and run this. Okay. Now that took a little while longer than it normally does. I don't know why, but Control-C, run again. There you go. So it's almost 20 milliseconds faster. That is to say, 21 thousandths of a second faster than the number we had before. So this is now at 74 thousandths of a second to start the application and be running and serving traffic. That's interesting, but of course, one of my favorite things to do is to measure resident memory, right? So, puke up AOT, that's the PID, all right? And I want to measure that by using a script. This script will print out the resident set memory of the binary given the PID. So I'll run that with the PID that we just captured. And you'll see it's taking about 103 megs of RAM to run on my local machine. Amazingly, as good as these numbers are, I'm running on a Mac, and I found them to be consistently better on Linux. And I have to wonder if it's just because I put less resources into the Mac, or maybe it's because I'm running on Apple M1. I just don't know. But I can actually get a Linux binary running in a Docker container on my Mac M1 to run faster than I can with a native Mac binary natively on the Mac. I don't understand how that's true. Don't ask me to explain it. I don't know. I've just found anecdotally it's very fast on Linux. So this is as good as this is. And remember, we're running this for with 100 megs of RAM. Most applications, I think, if we're honest with ourselves, most applications on the JRE take anywhere from 512 megs of RAM to a gigabyte of RAM, and that's a lot, right? It's a lot if you can get it down to 103 with much smaller RAM footprints. This is a tenth of your typical JRE deployment. That's an amazing situation to be in if you're being metered
and are being charged by your resource footprint. So far, we've created a brand new Spring Boot application. We did absolutely nothing to accommodate the fact that we're going to get a GraalVM image. We are using the new Spring Boot 3.0 and Spring Framework 6 baseline, which implies a Java 17 baseline. And we're using GraalVM. And we now have the foundation on which we can explore more of Spring's AOT.
Spring AOT system is a new level of integration between your code and the compiler. Now, we'll explore this in great detail a bit later, but you should understand that it gives you a way to reify some of the dynamic things that you might have otherwise done at runtime into code generated at compile time. This has the benefit of reducing things that can work against you at runtime, like reflection. I wish that I could say that this support is going to dramatically change the game for your application when running on the JRE, but it's fairly middling, right? It's not going to be a huge thing. It might be whatever, 10% or something like that, right? In my experience, we're talking about not negligible, but not huge amounts either. I haven't really checked, transactions per second and so on, but for startup speed, basically, it's not going to be a huge win there on the JRE. I have no doubt that there's an advantage there, of course, certainly in terms of memory footprint and so on, but I just don't know off the top of my head how big that is. Instead, the AOT mechanism really comes into its own when it comes to building code destined for a native environment like GraalVM. We've looked at a lot of different things in the GraalVM universe in the last couple of years. You've been watching me do Spring Tips videos introducing the latest and greatest in the AOT world for at least 2 years now. The bulk of that history has been as we introduced our R&D Skunksworks project called Spring Native, which we started building a year or so before I started talking about it in early 2020. We've looked at the ever-changing story with GraalVM and Spring over the last few years a number of different times. The bulk of those videos has been in me introducing Spring Native, our R&D Skunksworks project, which we started building a year or more before we first started talking about it out loud in early 2020. We've looked a lot at the ever-changing story of GraalVM and Spring over the last few years, and the bulk of that history has been in terms of our R&D project Spring Native, which we started building a year or more before we first started talking about it publicly in early 2020. We created Spring Native as a way to make Spring and its vast ecosystems of integrations work well in a GraalVM native image context. That work originally existed as a separate project which integrated with Spring Framework 5 and Spring Boot 2, but that now lives on in the new Spring Framework 6 and Spring Boot 3 generations. Spring Framework 6 and Spring Boot 3 are new generations of these frameworks. This is a big moment in our history here. For those of you that have been living under a rock, GraalVM is an open JDK distribution that was created by Oracle Labs and that features a new just-in-time compiler to replace Hotspot. It also ships with an ahead-of-time compiler that enforces a closed world perspective on your applications in exchange for incredible gains in speed. This ahead-of-time compiler was an extra, but now, for a lot of people, GraalVM is synonymous with native images, and so it shall be in this video. When I talk about GraalVM, I'm referring to its native image capability. The native image capability is amazing, but the closed world assumptions it makes can take some getting used to. You need to understand how the GraalVM compilation process works. After you've compiled your Java source code to class files, it takes your class files and all the class files on the class path and analyzes them, finding all the types that are explicitly used, basically starting from your main method and working its way outward. As it goes through all your types, it throws away anything it thinks that you are not using, that is to say, that it deems to be not reachable, and keeps only what it is able to find and what it deems to be reachable. But this is a static analysis done at compile time. It can't deterministically see that in some places subclasses will be generated at runtime. It can't see that in some cases there will be reflection done on various types. It can't know that your types are going to load resources from the jar's class path. It doesn't know any of this stuff. And when you try to run your application, it's going to blow chunks. Here is a non-exhaustive list of some of the things that GraalVM needs to know about beforehand in order for it to work. Things like resource loading, serialization, JNI, proxies, reflection, etc. You provide these hints in terms of configuration files that live in the meta-inf native image directory of your application, or any library on the class path. These files are JSON files. They're stringy. you'll need to account for all the things that might go wrong in your application. Obviously, Spring will furnish these configuration files for everything that it provides, for everything that it knows about. And as time goes on, and increasing many libraries are building and shipping hints for their released jars as well. Ideally, this code should live in and change with the projects themselves. But not all projects have the appetite or the resources to make these available. Or indeed, some are just, fallow. They've reached their useful evolution and nobody's actively working in it right now, even though they continue to serve a purpose. Thankfully, there's shared community reachable metadata that you can use to augment the default metadata that you've got out of the box. This is pre-written configuration for various libraries. It's a collaborative effort to which anybody with pre-written configuration may contribute. Again, the ideal situation here is that the project proper maintains these configuration files. But if it won't, then it's nice to know that the community could and should consider the maintenance burden. If there's no shared configuration and the library that you're using doesn't furnish its own, however, then it's up to you. Somebody needs to provide this configuration. You need to do this for every place that you intend to use one of these aforementioned features, things like serialization and proxies. And any place that any library does so with one of these things also needs to be accounted for as well. You could write these configuration files by hand and maintain them as JSON files that evolve in your code base. But what happens if your code changes and you forget to synchronize the JSON files? Spring Framework 6 and Spring Boot 3 are here to help. Spring Framework 6 introduces a component model that can dynamically generate the configuration for you at compile time. We'll explore that momentarily. Let's start at the beginning and the happy path where your code just works without any explicit configuration. Then we'll dive deeper into the component model and see how it interacts with the compile time phase. A factory object contains the complex construction logic for objects of a certain type. You might do this to handle situations where a number of factors may influence the final produced object. This is especially useful if you're dealing with more than one possible implementation of a common type and need some central place in which to decide on the correct configurations. Spring's factory beans serve this role, letting you feed in the parameters of the object that you want and getting the result as you specify. A good example of this, of course, is when configuring a data source, a javax.sql.dataSource, which might connect to any number of databases with any number of different connection pools and have any number of quirks with which to contend for each of these. We may need to specify any or all of these factors when we arrive at the final pooled data source that we're going to use in our production application. Hiding that configuration recipe behind a factory bean is a great idea.
Let's turn now to some fundamental things that you've probably dealt with before, just to make sure they still work as we expect. First up, factory beans. Now, of course, I don't use factory beans a lot these days, but you might, and it's just nice to know that they work. So factory beans configuration, and we'll create an interface here, void speak. We'll have a cat implements animal, and we'll have a dog implements animal. And again, same basic contract speak. So woof, system out, meow. Okay, so there we go. Two types of implementations, and I'm going to create a factory bean that makes it easier for us to create an instance of that, right? And the reason you do this, whenever you create a factory bean in Spring, is to hide the recipe for some complex construction, right? So if you have an object that has multiple parameters and multiple scenarios that result in different objects being created, then you might encode that in this recipe. This also used to be very good for encoding the recipe to create a new object in the world of XML, right? So application ready event, application ready event. Okay, I'm going to call this factory bean listener. Return new application listener. And we're going to depend on a bean of type animal. Okay, now what kind of animal? Well, we're going to create a factory bean here and have it produce that object for us. So animal factory bean, and then what are the properties that we'll use in deciding to how to vend it, right? And obviously these are completely arbitrary, but you get the idea, right? Like frisbees. Good. So there's some constructor arguments. You might have setters instead. Doesn't matter. You get the idea. And so we'll say true, it likes yarn, it does not like frisbees, okay? And so we'll say, okay, the type is this. For the object type, it's a type of animal. And we'll say, okay, return this that likes yarn and doesn't like the frisbees, then return new cat, otherwise new dog, okay? As a silly example. Now, obviously, this is a toy, but you can imagine a more realistic example, like, for example, data sources, right? Data sources, there's a data source factory bean that you can use to create a new data source, a connection to a database. This can be driven by any number of things. For example, the driver class name, whether you have load balancing enabled, whether you have SSL enabled, whether you're encoding username and password directly in the URL or you want to derive it from some other place. All these things come into play before you can get a javax.sql data source. So you want to hide that logic inside of a factory bean. Let's go ahead and run this code. So there you go. The application started up and it printed out meow. So that clearly works. I defined an animal factory bean, but I consumed an animal, the product of the factory bean.
Spring beans have different scopes. Most objects are created but once per application, but some are created anew for every new request, for every new session, for every new thread, or indeed every injected use of the bean. Spring beans are bound to a scope by default. That scope is singleton, which means there's only one of them per JVM per lifetime of the application context.
Next up, we'll look at scopes. Now, scopes are a very old feature, so you shouldn't be surprised by their use, but let's take a look. We'll create a configuration class, and we're going to create a bean that, let's just say context HTTP controller. Okay, I'm going to call this at controller at response body, and it's going to in turn make available a pointer to a Spring Bean called request context. I can't think of a more imaginative, useful thing. And this will have a scope, and this scope will be scope request. Now, of course, it could also be scope session, right? You could do that. Lots of different options here, scope application, etc. But let's, for our demo, let's just make it scope request, and we'll have a field here equals uuday.toString, okay? And we're going to have a getter. So when somebody wants to request that state, it's created once the bean is initialized, right? So I'm going to inject a pointer to a request context object for the current request, but of course for every request you'll have a different instance. And then here we'll just say scopes context, okay? String uuid, return this dot context dot get uuid. Okay, now I'm injecting a bean into the constructor, but I don't want to initialize it until we're actually in an HTTP request. So let's just leave it at that. We'll go ahead and restart the application. All right, there it is. Let's go ahead and curl that endpoint now. So localhost 8080/scopes/context. There's 1, there's 2, 3, 4, 5. So again, for all outward appearances, I'm just creating one Spring Bean, and I'm injecting a final reference to it, and I'm just referencing the same getUID method from that injected bean, but because it's got a scope, it's bound to the current lifecycle of the current HTTP request. And so this is great. For example, if you have a session bean, you could keep your user's application, a shopping cart or something like that, whatever. The point is, this just works, and there's some insane stuff required to make this work. There are other scopes for things like threads, for sessions, for whatever. In fact, Spring has an extensible SPI that you can use. So I've implemented a couple scopes in my life. Spring Batch has a scope. Spring, scopes are found in external projects as well. So, for example, the Flowable workflow engine has a scope as well for processes. Lots of different options here, but the point is it just works.
what happens when you have more than one implementation of a given type? Suppose you do have an interface of some import and you have different implementations. Qualifiers work as a way to disambiguate which bean you want injected when you'd otherwise get conflicting versions of the bean. Let's take a look.
Another very commonly used feature in the Spring component model is qualifiers. So let's just go ahead and create a qualifier example here. Qualifiers configuration, and we're just going to create an application that manages an app store contract. Okay, so let's say we've got interface app store, or whatever, mobile marketplace or something like that, right? And then interface iOS app store implements, I guess we could say class implements mobile marketplace, class play store implements mobile marketplace, right? So now we've got different beans, doing different things here at service. And I want to know what I get. So let's create one listener here for application ready. So we'll say iOS, and I'm expecting the mobile marketplace implementation here. Okay. System out mobile marketplace, .get class .to string, right? That's the generic version. And I want a similar thing for Android, right? So we'll say Android. So I've got two beans that both have the same interface. Normally this would be a problem for Spring because it can only inject by type or by name or by some combination thereof. But you can actually disambiguate which one you want by using the qualifier annotation. So I can add @qualifier, and this would be iOS, and this would be Android, right? And I could actually use those qualifier annotations here. So Android. Now you can go a step further. You can actually create meta annotations. So for example, @interface Android retention is what do we care about? We want runtime @qualifier Android. Okay, and then iOS or Apple or whatever, right? iOS, I don't know, whatever. I like Apple better. Okay, so there we go. There's our two annotations, and we can use that. So as long as the beans themselves have a qualifier and the injection site has the same qualifier, they'll match, and that's true even if, for example, we use @Apple here, but we don't over there, right? As long as they ultimately resolve to the same qualifier annotation, then it works. So Android and Apple. So when we run this, we should see the different classes reflected in the output here. But let's go ahead and compile this and find out. So there you have it. The application is started up, and you can see that one callback injected the Google Play Store, and the other callback injected the App Store, right? And that just worked, and there's no errors and no problems about there should be at most one bean of this type or whatever. That said, it is also worth noting that Spring has a mechanism for you to inject, more than one bean of the same type. So mobile marketplace listener. Here you can actually inject a map of the bean names to their implementations, right? So like this, marketplaces, and then do whatever you like, right? So mobile marketplaces dot for each key bean system out key equals bean dot get class dot get name. Okay. Let's restart this and rebuild. Aha, there you go. So you can see We've got the bean name on the left and the implementation on the right, and that also works in the AOT native image context.
Let's take a look at Spring Boot configuration properties. Moving slowly up the stack, Spring's environment object makes it trivial to configure applications with configuration, which it sources from any number of property sources. These property sources understand things like HashiCorp console, environment variables, HashiCorp Vault, JNDI, the Spring Cloud config server, application.yaml, etc. Right? Basically, they're a strategy to resolve configuration from an external place. And when I say configuration, I mean values, keys and values, strings like .ini properties or .properties files of your. This is all, of course, well supported in Spring Framework 6 and Spring Boot 3.
Moving up the stack a little bit, Spring Boot has this mechanism for binding property values from the Spring environment to job objects. So let's check that out. Okay. We're going to create a properties configuration class, and we'll define some properties here. So we're going to call these demo properties, very boringly. And we're going to say configuration properties prefix equals beautiful, and we're going to enable configuration properties for this. So we'll say demo properties.class and @bean application listener application ready event properties application listener demo properties.name. Okay, so the name is, and of course for this to work we need to bind these properties to the object by providing a value for them. So application.properties beautiful.name equals world, right? Or Spring Boot 3 AOT. So beautiful.name should be bound to that property, and it should be available so that we can dereference it as a job object here. Let's go ahead and compile that and see if it works. All right, when we ran the application, yep, it compiled just fine. Nothing required to make that work. Spring Boot auto configuration properties or configuration properties work just fine.
XML. XML is an amazing thing. Our goal is to make it as easy as possible to take an application built on Spring, upgrade it to the latest incarnation, and make that work in the new and native Spring Boot 3 world. A long time ago, people used XML to wire their Spring applications together, and Spring's AOT engine supports that too. So yes, XML works too. Let's check out a simple XML example.
Went up the stack a little bit. Let's go way back down and look at an old friend, XML configuration. We'll create a new package here called XML, and I'll create a new config file that really we're not going to use at all, right? It's just going to serve to import the XML. Okay, so import resource. I'm going to call this XML, app.xml. We'll create a new file in there called app.xml, beans, spring, blah, blah, blah. Okay, UTF-8. And then beans. We'll paste those namespaces in because I don't remember how to do this. It's been a long time. And then we're going to define a bean. Well, what kind of bean, you might ask? Well, let's go here and create a logging, XML logging application listener that implements application listener, application ready event. And we're going to need a pointer to something that we're going to create here called a message producer. Implements supplier. Okay, just as an arbitrary example here. And we'll say return hello world. Good. So these are both beans, and we want one to have a reference to the other. So message producer, and we'll say this dot producer dot get. All right, and we're going to print it out. The message is message. Okay. Now, of course, this we're going to inject in the constructor, and we need to configure two beans, one that has a dependency on the other. You know, we could do constructor injection, but I kind of miss setters. You know, so private message producer nullable, right? And we'll have a setter here. And then in our XML, we're going to define this relationship. So go here, we'll get a bean of type XML logging application listener, property ref producer, ref equals, and then we'll need a bean of type message producer, and we'll point it to that. So we'll call this name is going to be message producer. Is it ID or name? I never remember. Maybe it's lexically scanned. I don't know. Let's see. That, please. Yeah, that looks right. Right? Doesn't it? Kind of looks right. Yeah. IntelliJ thinks it's okay. Okay, good. So we've got this message producer, and we've got this bean, but notice that neither of these beans has any annotations on it, and they're not explicitly registered here. So the only way Spring will discover these beans is if it's correctly reading in the Spring XML application configuration file. Let's go ahead and try this out. Okay, the message is hello world. And what does message producer give us? Capital H, hello world. Capital H, hello world.
Thus far, we've been taking a tour of some of the fundamentals in Spring Framework and in Spring Boot 3 to kind of remind you that the Spring component model is rich and dynamic and supports all sorts of different use cases. And everything has worked flawlessly so far. And that's certainly our goal, that the vast majority of Spring applications have a path to upgrade to Spring Boot 3 and then enjoy the benefits of GraalVM native image compilation. But sometimes things don't work as expected. Sometimes they don't work because one of the libraries on the class path, or indeed your code itself, has done something to run afoul of the aforementioned use cases where we'll need to furnish configuration files or JSON files.
All right. You know, it's important that we look at ways to identify where you're going to need to provide configuration. So let's introduce a simple example. We're going to call this migration. So we'll create a class here called migrations configuration. We're going to need that. And I'm just imagining a scenario where we have some data in a CSV file, let's say. Okay, so data.csv. And in this data, I'll just have some names. So, my name, hi, who else? Awesome people on the Spring team, and me, right? In no particular order. It's awesome people and me. Madura, Olga, Yushin, Violetta, who else? Spencer, 9, Chloe, 10, whatever, right? I mean, there's a lot of different names here, Dr. Sire, some names, okay? Now, I want to read these in. So that's a CSV file, right? So I'm going to create an application listener, listening for application ready event, people listener, right? New application. And of course, I'll create a DTO for a person, string ID, string name. And what else? I'm going to get the contents. So try var, I need the contents of the resource, the data of the file. So I'll use Spring to give me a class path reference to data.csv as a resource file, as a resource object, right? A Spring Framework resource. And I'll just inject that. I'll say try var in equals new input stream reader csv.getInputStream, and I've got that. And of course, this is a try catch kind of scenario, isn't it? So add sneaky throws from Lombok so that it basically quiets that. It's a runtime exception now. And with that, I'm going to copy the data into a string. So CSV data, and I'm going to turn each of the lines into each of the, I'm going to turn the string into lines by dividing by its line separator, by splitting by that. And then for each line, I'll turn it into columns. And then for each row, I'll turn it into a new person. All right, so a new person, row 0, row 1, and then, just so we have an example of reflection, let's now log those out using the object mapper from Jackson, right? So for each of those people, we'll use object mapper dot write value as string, passing in person. Now, of course, this also requires a checked exception. So I'll do this out here. Okay. And so now I've got this method decorated with sneaky throws, and we don't need this anymore. Rename it to, JSON. Okay. So let's turn it into JSON, and then for each JSON, we're just going to print it out. Okay, so all I'm doing is, it's pretty pointless. I'm reading in the data as CSV, and then turning it, turning right back around and writing it back out as JSON data. And this is going to require, naturally, I shouldn't have done that. I want my checked exceptions to go away. Okay, so I'm turning that back around into JSON, right? So I'm logging it out. Okay, good. So you can see the problems here, right? First of all, I'm going to run afoul of GraalVM because I'm loading data from the class path, the resource, as a resource. I'm trying to do the equivalent of class.getInputStream. And then also I'm doing reflection, right? Or rather, Jackson, the object mapper, is doing reflection to take this person and turn it into a JSON string. Both of which are bad, right? Well, they're not bad. They're just problematic. You need to account for that. So what tools do we have at our disposal to kind of figure out what needs to be done? Well, obviously we can guess, but let's just take a look at some tools that you might use, or in particular one tool that you might use for larger scale efforts where you've got a lot of code that's untested, unknown, and whose configuration you just don't know about yet, okay? All right, so we've got the application code ready to go. Let's plug in this Java agent. pom.xml, and then we're going to paste this here. This is going to set up an agent lib called the native image agent, which has a parameter called the config output directory, which has as a value target native image. That is to say, in the target directory under native image, it's going to dump out the configuration files that we would then need to make our application work. And so this has to, you need to run every interesting code path for this agent to pick it up and help you out, right? So a good place to put this kind of thing is in the build pipeline. All right, let's go ahead and run this. So we'll do rmrf target and maven skip tests clean package spring : boot run. Okay, the application started to run, and it's done everything that we wanted it to do. So we'll hit Control-C, and then we can go inspect the target directory. And you can see there's the native image folder. And, all the configuration files that we might conceivably need. Now, of course, this is going to be a lot more than you actually need, right? Because again, Spring Boot and Spring Framework will take care of a lot of this, if not most of this for you. All we really care about is the stuff that's unique to our code. And so we care about the person being declared there, right? Common example, AOT migrations person. We care about anything, with .aot migration. So obviously this stuff is going to be unique per run, right? This is all cglib stuff generated randomly by Spring. So you don't want to write that down. You don't want to provide the configuration for this because this is not going to be the same name as you get next time. The memory will be different, etc. So what we care about is this stuff that we created that Spring won't otherwise know about. So it's not going to know about this type because we're not returning it from any controllers. We're not using it in any Spring data repositories. Indeed, there's no connection between that and any of our Spring mains at all. And certainly, even if there were, it may not be the case that those things are requesting as fully featured permissions for reflection as we require. Here, we want all these things, right? So there's one type that we care about. We also care about the data source, the CSV, right? That's a resource. And you can see that, Spring has already registered a bunch of other things. And you can see if Spring does class.forName, or if something does class.forName, that's a resource. You're loading a file, turning it into a class, right? So you have to care about that. We have the XML. We loaded the XML earlier, so that worked. But what we care about, of course, is anything that we added, like data.csv. So there's that. So we need to teach our application about those two things. Let's start with the reflection. That's the easiest. We can just use an annotation. Register for reflective binding person.class. Okay, so that'll actually just, for your application, for business level applications, whatever, this might be enough. Maybe you have a couple types here and there that just need reflection, and that's it. Everything's fine otherwise. Okay, good. Just use this annotation. It's easy as can be, and you're done. But if you want to register any of these other hints, and you will need to have more granular control, then you can just, if you need to have more granular control, then you can create a runtime hints registrar. So migrations runtime hints registrar implements runtime hints registrar. And this is just a callback interface, and you get a pointer to the hints type and the current class letter. So here I could duplicate what I did for person.class like this, and I can specify what kind of access I want, right? Do I want all the classes, the fields, etc.? And you can do more than one of these, obviously. I like to just do .values. That gives me everything, and that's more than likely going to be too much, right? You probably don't need that, but in that first pass through, I like to just get everything so I can make sure it works. I'd rather have everything and then move on, knowing that I've gotten everything I need out of that, and I can face the next issue. Then, if I have time, when I have time, I come back and I'll try and reduce the things I'm asking for here, the surface area of my request. Okay, so this is duplicative of the register for runtime hints. I don't need it, but now you could do it if you wanted. What we do need, however, is to register that resource. So here, I can register a string, or if I have access to the shared resource, remember that I used a class path resource? Actually, I used a resource here, right? This is a add value annotation on a type of resource. Well, Spring is going to look at the schema of the URL, and it's going to create an instance of this, a specialized instance of this called the class path resource. So if I had access to that same type, that same variable, I could just pass that in, right? And this is effectively the same thing, but there's no need in this case to do that. I don't have access to it, so I'll just register the pattern instead. It's the same thing, right? It does absolutely the same thing. And then finally, I have to register this. I have to import these runtime hints. Okay, and this is, you put both the register for reflective binding and the import runtime hints on configuration classes or bean provider methods. And that's right? You could actually have runtime hints that live on this bean definition instead. So maybe for this bean and all the things I'm going to do therein, I need this runtime hints class. But for another one, I have a different one, right? And again, if you're building your own organizational auto configuration, again, you might use this as well. You might have that there. For cleanliness of your workspace, your namespace, maybe you make this a static inner class, and that works just fine too, right? You don't have to make it public and all that stuff either. It's just a regular class, like like you've always done. So now, from the outside perspective, your API hasn't changed, only the implementation details, and that's hidden, or at least very clearly not meant to be used from the outside. Okay, so let's go ahead and compile this application and use it. So let's go ahead and compile and run this application. So we'll do Maven p native clean package. Okay, it's built. Let's run it. See what we get. Ah, there we go. It worked. So we have our JSON reflected here in the console with very little pain indeed.
So you can see the Java agent and the surface level component model provided by things like runtime hints registrar and register for binding are great ways to identify and plug the holes in your GraalVM native image. For a lot of developers, these two tools, the Java agents and the hints, may be enough to get the job done. And this is hopefully as much as most application developers will need to know. Things get more interesting, however, when you start to imagine infrastructure level concerns and when you start looking at purpose-built frameworks built on top of Spring Boot. Let's put our infrastructure hats on here and take a look at some of the meta model programming that Spring has supported since day one, and then look at how all this new AOT compilation stuff interacts with all of that. We looked at XML earlier. If you're new to Spring Boot, then you've probably never dealt with XML configuration format of yore, more typical of applications built before Spring Boot. It's interesting in this context because it demonstrates that Spring doesn't care how you define the wiring of its objects. You can define that wiring, the relationships, the ontology of those objects in XML, or using component scanning, or using Java configuration, or functional configuration. If you've ever used Spring Foo, then you know you could also define the wiring explicitly. Did you know that there was a way to define the wiring using .ini files like a long time ago before Spring 1.0? That's true, right? It's because the source of this configuration all gets canonicalized into a meta model. Spring reads some sort of input and then arrives at a meta model containing bean definitions. These bean definitions contain information about your objects, how they relate to each other, their dependencies on each other, their properties, their constructors, etc. At this point, you have a bean factory full of bean definitions. This is the primordial soup of your application. You can register beans of type bean factory postprocessor or its various subclasses to act on the bean factory, replacing bean definitions or contributing new bean definitions as you go. As an example, the original use case for Spring Cloud, before we turned it into a microservices framework that we all know and love, was as a set of connectors for cloud platforms. You would add a appropriate binder to your class path and then deploy the application to your cloud infrastructure of choice, like Cloud Foundry or Heroku or whatever, and it would see that you've got an local host H2 instance, for example, as a data source, and you would see that in that Cloud Foundry context, you've got access to a Heroku or a Cloud Foundry data source, and it would dynamically replace the bean definition for your data source with the one in the cloud provider in the context there. It's also possible to create whole new bean definitions at this point. Before Spring Boot's auto configuration and the functional configuration in Spring Framework 5, working with bean definitions was one of the easiest ways to analyze and hydrate object graphs based on cues from the developer, as you might want to do, for example, with a framework like Spring Integration or Spring Security. Let's look at an example of a bean factory postprocessor.
Let's look at bean factory postprocessors. We'll create a new directory here called bfpp, bean factory postprocessor, and we'll create a new class in here called bfpp configuration. And it's just a configuration class, as all of our examples have started off. And everything we're going to do in this example centers around a listener. Okay, so an application listener, application ready event, and this in turn will implement the on application event callback, and it'll use a Jackson object mapper. Okay, and we're going to inject that into the constructor like this, and it's going to work with, let's say, a product. Okay, just a type that we've got, and I'm just going to log out some products. Okay, list.of new product uid.random.toString. Good, and just for each one of those, for var p product law, system out, and then we're going to use our friend the object mapper to write this value as a string. And of course, this will throw an exception. We'll make it a runtime exception. Okay, so I've got this bean, and you can imagine what it's going to do. I'm just going to create two objects and reflect over them using the Jackson object mapper to write them out. So we need to register this bean factory post processor. Obviously the most logical way to do it is just to create a configuration class and create a bean and so on, or just put add component, right? Like that would be fine too. But there is a way to remix the application context, the bean factory, early on, right? And so we're going to create one of those. We can create a, let's say, BF. Maybe we just call this listener. We just call this BFPP. We're just going to call it listener BFPP, or listener bean factory post processor implements bean factory post processor. Okay, so this is a very early callback, and you don't get a fully formed context yet. You get a bean factory, and you can do things like register a bean in that bean factory, and you can inspect it. You can say B factory, give me bean definition, blah, or you can enumerate all the bean names. So bf.bean definition names, and then for that, you're able to get a pointer to a bean definition. So bean definition equals bf, get bean definition, bean names, etc. Maybe that shouldn't be names, just singular. Very good. And I can inspect the bean definition and get the bean class, resolve all types, they depends on the initialization method, etc. I get the bean class name as a string, right? The class may not even be ready yet, right? We don't even know that for sure. So all this stuff is kind of like stringy, but it gives you enough to do what you need to do at the early startup of your Java application on the JRE. And you can actually, programmatically register things and so on. So I'm not going to log out every bean definition, but you could do that. We could also say, I want to get a bean definition. I want to register custom types, singletons, etc. But if you want to programmatically add a bean definition, there's a subclass of bean factory post processor called bean definition registry. Okay, post processor, and this bean registry you get a logical chance here, a logical opportunity in this implementation to post process the bean factory, and basically this is downcast to a bean definition registry. Okay, and in our case, we don't actually need the bean post processor behavior anymore. Right? We're not doing anything interesting in there. We're going to do our work in here, but we do have to implement this because, again, this extends bean factory post processor. So I've just got this empty thing here, and what I want to do is I want to programmatically register an instance of our type, right? So this gets changed here. All right, so I'm going to register bean of type listener. What bean name should we give it? Well, how about we just put that here, string bean name equals my BFPP listener. Okay, whatever, it's the same. As long as it's relatively unique, you could do that just to be sure. Just make sure you use the same random one per run. Okay. But yeah, we don't even need that. We can just leave it like this, whatever. And we are going to register bean if it doesn't exist. So if registry.contains bean definition, bean name, right? Good. If it doesn't contain it, then registry.register bean definition, bean name, and we'll use bean definition builder.root bean definition, and the type, let's just keep things interesting here, will be the fully qualified string name of the type, right? So as far as the compiler is concerned, this class is never used. You can even see my IDE is saying it's never used. Well, of course it's used. Spring is going to start up and it'll create an instance of this bean, and that will exist in the application context. So this will actually all still work. Spring, you don't have to do anything to make this work. But we do have these products being used, and we're reflecting on those types. And so we can infer that if this bean is present in the application context, that therefore we're going to need to register some hints. So there's a second interface here called bean factory initialization. So listener bean factory initialization AOT processor. Okay, bean factory initialization AOT processor, and the callback there is kind of analogous to the bean factory post processor hierarchy. It's very early on in the initialization at compile time of the application context. So you get a chance here to modify the bean factory and to write hints dynamically based on it. Okay, so I've got a bean factory there. I need to return an instance of bean factory initialization AOT contribution, and there I'm given some pointers to some interesting stuff. One thing that's really kind of powerful is code, right? And we'll talk about that in a second. But basically, you can do code generation. You can generate new classes as a result of your analysis of the bean factory at compile time. You can say, remember what I just said, you can actually get the bean definition names, right, at compile time for var, bean definition name, etc. You can do all the kind of stuff you just did. You can also check to see if something is registered, which is interesting to us. So here we'll say, hey, if this contains this bean definition for bean name, then we want to return this. Otherwise, we turn null. So we don't care to register or do anything with the AOT context unless that bean is present, right? This bean factory initialization AOT processor is only concerned with this particular component. Obviously, you can register as many of these as you want. So here, if that bean exists, then I know that there's going to be trouble at compile time. At runtime, because of the products, right? These things down here that we're reflecting on. So we need to make sure that we contribute hints, and we can do that by getting the runtime hints here, right? So you've seen this runtime hints before. It gives you a chance to call, register for type for product.class, member category.values. There we go. So I'm just registering hints, but I'm only registering hints if the bean is there in the first place. If it's not, then, why bother registering the hints? They'll just bloat the runtime heap, the native memory of the application, okay? Good. Now, we've got this bean factory post processor. Spring, this is you can register these a number of ways, but if you use bean configuration, remember they have to be static, okay? These get invoked, like I said, really early on, before Spring has got live references to actual objects. It's just got these static methods, and so here you're telling it, look, I'm going to register this interface. It's going to be involved in creating, sculpting out of the ooze of our application context a really, a real fully formed application, right? And so that gets invoked this way. This is very convenient. What about our AOT processor? Well, it's just a regular Spring bean. This doesn't require anything special. You can just do this if you like, right? That works. There is another way, however, and that is to create a folder here and register it in the service loader. So metainf spring new file aot.factories, and here you can put any of the common AOT interfaces as entries, just like you would for auto configuration and the like. So aot.factories, put that there, and then our implementation is here. Okay. So this is our listener bean factory initialization AOT processor. And there's only one entry. Obviously, if you wanted to, you could have a common delimited list. There's our AOT processor and our bean factory post processor. There's nothing stopping you from putting these in the same component, right? Obviously, this one class could implement both bean definition registry post processor and bean factory initialization AOT processor, in which case you wouldn't need to register them twice. You could just use the static bean definition, and they would both be involved at the right lifecycle phases, right? And that would be fine. And that way you can actually share the bean name, right? I've got the bean name in a single common place so that both of these individual components can get access to them. But, maybe you want that parameterized. Maybe you put that in the constructor here. Whatever. The point is, you can register these types in a number of different ways. So let's go ahead and compile this application and run it. And we'll see it's going to create an instance of this. It's going to then programmatically reflect over these types, and then hopefully that'll all work. Maven, skip tests, p native clean package. Okay, let's go to the target directory, AOT, and there we go. Everything has worked just fine. Do we see the products? Customers. There it is, 2 products, SKUs. Okay, so that has worked mercifully, right? All because we're able to write these bean definition registry post-processors in conjunction with, often but not necessarily, these bean factory initialization AOT processors.
When you compile an AOT application with the Spring Boot, Maven, and Gradle plugins, a few things happen. Your Java code is compiled into .class files. Your .class files and all the libraries on the class path are then ready to use in the JRE. The Spring Boot build plugins then create a version of a bean factory with all the correct beans and components in place, but it doesn't start that bean factory. It doesn't start the beans themselves. So at this point, you have a bean factory full of bean definitions with no beans, no actual concrete running beans. A bean factory initialization AOT processor runs at this point in the lifecycle at compile time before the objects have congealed into fully formed and running applications. You still have access to the bean definitions, but just as with the bean factory post processor, you should not access or try to eagerly initialize the beans themselves. It is here you have an ideal chance to inspect the bean factory and contribute whatever hints that you'd like by looking at the bean definitions in the context. Remember, at this point, you don't even have actual objects or beans, just bean definitions that'll eventually become beans. It's still enough for you to inspect the types and find out the class and the reflective metadata about the class to get your job done, however. Maybe you have many objects that will benefit from the same set of hints. You can register them here, and be sure that the hints will be contributed only once per bean factory. Now, in truth, this gets normalized. It gets deduped by GraalVM itself. So multiple redundant additive contributions of the same hints will only result in one actual hint, which you can use to your advantage, actually, because you can actually have different things that add to the definition of a single set of hints. Remember, these bean definitions are what result after all the configuration classes and XML configuration files and component annotations and all the component scanning and the functional configuration has all taken place. These channels use a lot of reflection, which we want to reduce. The AOT support in Spring goes to great lengths to capture the state of the beans once they're created in that compile time bean factory and to preserve them, to reify them at compile time so that when the application starts up, it can skip all that reflection and resolution and configuration and searching and so on. It does this with code generation. The bean factory initialization AOT processor can process beans in whatever way you'd like, adding whatever bean definitions you'd like, including new classes that you've written out dynamically using the code generation API. A ton of what Spring does at runtime can happen at compile time by this source code that you generate. Remember that we saw the bean factory being assembled with a static method earlier on. That was all thanks to this dynamic code generation capability. This approach of capturing the build time state and preserving it for runtime and short-circuiting so much of the runtime recreation of that state with proxies and reflection and all is super useful. And as I've said a number of times, it has some interesting implications. The bean graph is frozen at compile time. This means that nothing new can be contributed at runtime. It's fixed. Now, before we can continue our tour of Spring's component model, let's take a brief look at the library that powers some of the code generation facilities in Spring Boot 3, a project from Square called Java Poet. Now, let's take a brief look at the library that powers some of the code generation facilities in Spring Boot 3, Java Poet from Square. In the last example, we looked at the bean factory initialization AOT processor, and we saw
that you can register hints at the very early compile time phase. Well, I also alluded to the possibility that you could do code generation. Code generation is supported, as we talked about, through a project called Java Poet. And before we move on, I want to take just a quick beat and explore some of that, right? So let's create a little test here, and you can see some of the possibilities. Okay, so Java Poet, and we'll create a new Java Poet test, and it'll just be a regular old test, nothing too special about it. And what I want to do is subclass something dynamically at compile time. Okay, and I'm going to use Java Poet to write the code to do that for me, basically. So we'll say that we have a method that does a subclass, so private type spec, right? And this is, notice that we've vendored it. It's now part of Spring Framework itself. We packaged it basically. Target. Okay, so there's the type we want a subclass, and we'll return null for now. Okay, and then we'll have a Java file. So we're going to say, okay, actually, type spec equals subclass. Type spec, and we're gonna subclass what? Well, how about this? Let's create our own customer service, and we'll have a record called customer, integer ID, string name, whatever, right? And let's add some methods. So, customer save string name, return null, who cares? Another one to, I don't know, customer delete, no, get by ID, there you go. Just by ID, why not, who cares? Okay, so integer ID. So we've got two methods here, and we want to create a class that'll subclass that for us. Okay, so customer service dot class, and this type spec, I'm going to have to write it out into a file. So Java file equals Java file dot builder customer service dot class dot get package name, and then we want the type spec. Okay, and then want to build it. Okay, what else do we want now? And I guess we just want the code, right? So we'll say Java file to string, and we're just going to print it out. Okay, so code. Good. So that's the basic harness of what we're trying to do. Let's actually make it work. Okay, what I'm expecting is subclass of this that overrides all these methods. All right, let's do that. So for the type spec implementation itself, we need to start thinking about some practical limitations of Java, right? I mean, all languages have things like this. One thing is we want to make sure that we're not trying to subclass a final class, because obviously that will never work. So Java lang reflect dot modifier dot is final, right? Target dot get modifiers. Okay. The class can't be final. Oh, good. Okay. So good. Moving on. We also want to get all the methods. So methods equals stream dot of reflection utils get unique declared methods target and unique declared methods, and then we want to filter, right? We've got the methods, so filter the method based on certain qualifications, like for example, Java lang dot reflect dot modifier is private. So if it's not private, then we're okay. We'll go ahead and try. Okay, good. And what else? We want to make sure that it's not an object method, and there's a special method here in the Spring Framework Utilities class, so we'll just use that to make short work of that, because there's no point in trying to we don't care about overriding to string or something. You can do it if you want, but I'm not going to override that. Nothing I can do there usefully anyway. And then I want to map each method into a method. I want to actually generate the subclass for that, for the method spec. So I'll say we have a method here, private method spec, and this will be for a Java-lang reflect method. Okay, return null for now, and we'll say method spec m. Okay, and I think that'll do. So toList, and that gives us our methods, and then obviously we have to implement that method spec in a second, but let's keep going before we focus on that. So we got all the methods now, and we now want to generate the new type itself to contain all this method. So type spec dot class builder target dot get simple name plus subclass, whatever. We're going to build a dynamic subclass and give it a sort of infrastructure-y name there so that most people won't have any collisions with it. We'll make it public. And I'm going to get all the interfaces. I'll say stream of target.getInterfaces for each interface, right? For each interface, I want to add that to the definition. So new type dot add super interface. iFace. Good. Okay. And then new type, the superclass, of course, will be the target, and new type. I guess that's it. Then we want to add the methods, right? So methods dot for each new type add method. So we're going to add the method gets returned for that method to our new type. Okay. And then that, I think, is it. So new type dot build. Now we have to actually go through and implement the methods themselves, the actual method specs. Okay, so we've got this method. Now here, we're going to create a new method, var new method definition equals method spec dot method builder with a method dot get name, adding modifiers for public, adding modifiers for, I guess we don't need anything else, returns, method dot get return type, and adding annotations. Okay, and the annotation is just override.class, obviously. Okay, good. So that's the basic definition. Let's add some parameters, right? So param names equals stream dot of method dot get parameters dot map param name equals param get name. Okay. So new method definition, add parameter, and pa dot get type with parameter name. Okay. Good. And return param name as a string, right? And we get this whole thing as a list. So we'll have a list of strings as well. Good. And the actual body of the method we have to write out. This is a little bit of string templating or whatever. It's not going to hurt us. Statement is string.format, super.ll. Okay, so what have I done? I've got, I'm using Java Poet's nice template format. So this is actually a string format mechanism, but there's actually these $Ls get processed and honored by Java Poet later on. Okay, so here I'm going to say method dot get return type dot equals void dot class. If it's void, then we say that, otherwise we say return. So the last line is either going to return something while calling super, or just call super and not return anything if it's void. Okay, so it's going to say either space super blah or return super blah, right? Okay, it's just a very simple return statement there. And we'll say new method definition dot add statement, return statement, and we're going to have the method dot get name, and that's, I think, oh, we need the parameter names too, right? So spring utils dot collection to delimited string param names. Good. Okay. So I'm adding a statement where I'm returning or I'm calling super.l. L is being is the method name here, right? That's the first thing that's being formatted into this string by the add statement method here. So the string format template goes in there. First $sign L, which stands for I think it means lexical. Like it's just a regular. It doesn't get and translated. You put that in there, and then the second part is the parameter name, which is this. So I'm going to give it a list of the parameter names. So basically, I'm going to call super, taking in the parameter names that have been given to me, and then passing them into the super version, right? And I think that's basically it, right? That ought to do. So new method definition dot build. Okay. All right. Let's see what this gives us. I think we're close. Cool. So there's our class, customer service subclass that extends customer service, and it's a implementation method version of it. It's just calling super for all the default ones, but now you could put yourself in between. You could do something before, do something after. You could do all sorts of things if you have the ability to write code at compile time to augment what you've already got there. So imagine gRPC or something where you want to create converters or whatever. Maybe any kind of encoding I think would be very useful for this kind of stuff. Any kind of code that does anything with binary serialization is going to be useful to have this dynamic capability, right? Where you don't have to do this at runtime. Infrastructure kind of code, right? Stuff that we would normally do with JDK proxies at runtime, you could probably get away with doing it here at compile time. Now, don't get me wrong, you're not going to have to do this a lot, but it is nice to know that you can.
Java Poet was a code generation API that was created by Square in 2015. They assert, rather usefully, that so much of the interesting things that Square is able to do, particularly in the mobile space, with things like Dagger and auto value, is thanks to the magic of code generation. However, that code generation can be a little clumsy, and so they put together a program, an API, a library called Java Poet that gives you a clean, fluid DSL style way of writing Java code using Java code. It also takes care of things like if you reference a type to make sure to automatically add that type as an import at the top. Hopefully, this project seems useful to you because it makes it possible for us to very quickly write code that extends other code or works with other types in some interesting way. Now, of course, you shouldn't need to, but sometimes it'll be useful to know that you're running inside of a GraalVM native image. There are some properties that you can look at. Let's take a look at that. Let's look at a very convenient way to detect if you're running inside of a native image. Okay, so we're going to create a new package here called detection, in which I'll create a class called detection configuration. And it's just a regular Spring configuration class. Bean application listener ready event detection listener, and we're just going to print out the result, native detector dot in native image is native image. Okay, and behind the scenes, all this is doing is looking up this property or GraalVM native image code. If it's not null, then we can reasonably assume we're in a native image context. Okay, let's just run this application on the JRE before we turn it into a native image, and we'll see what it gives us. It says is native image is false. Okay, good. Now let's compile it and see what we get.
All right, the application's compiled and it's run, and now it says it is actually in a native image. So you can use this Boolean to tell your code, to inform your code that something is happening inside of a native image context. Now, you shouldn't do this very often, right? You shouldn't need to know about that, but there are some slight differences, obviously, particularly as infrastructure is concerned around what it means to run inside of the JRE versus to run in GraalVM native image format. So this is a good thing to keep in your tool belt.
These properties are available when you're running, and a lot of things in Spring's AOT support work by evaluating at compile time. I mentioned that these properties exist so that you might use them if you need, though we should hope that you don't need them. After all, you don't want to write code that works one way in one environment but differently in another. That'll be a divergence from the principles of the 12-factor manifesto, after all, which promotes the idea that you should have one binary that gets promoted from one environment to another. But we appreciate that the need may arise, unfortunately, to have code that is unique to your GraalVM native image version or your JRE version. Unfortunately, a few of the mechanisms that a Spring developer might reach for to create environment-specific builds or behaviors don't work in an AOT context. Consider Spring profiles. The profile mechanism works by letting you associate a bunch of objects, 0 or more, with a given tag, which is basically just a string, like a label, and then activating all the beans in that given tag when you start the application up at runtime. The objects only exist at runtime if they're associated with the default unspecified profile or with a profile that's been activated explicitly at runtime. This won't work in an AOT world. Remember, there are distinct phases, and the bean graph is fixed after the compilation. So unless the profile is active during compilation, the beans specified therein don't exist at runtime in the native binary, and thus can't be activated. So just avoid profiles altogether, right? Again, you can achieve a lot of what you need to do there by having things like bits of indirection, abstractions, things like that in your code, or just using the same properties and overriding them with environment variables and so on, and avoiding any changes to the code itself, the Java objects itself. The same constraints hold on for things like at conditional annotations. The same constraint, the idea that the bean graph is fixed after compilation, holds for things like at conditional and its conditions. Conditions are evaluated during compilation, so unless the condition is true when the application is compiled, it won't ever be true thereafter. For most applications, that's fine, right? And we can say that conditions work in AOT since there's no useful distinction in outcomes when evaluating the conditions at compile time versus runtime for most of the conditions that we know and love. So think of the usual suspects, testing whether a class is present or has another bean been defined. That's as true at compile time as it is at runtime. It'll always, in fact, be true at runtime if it's true at compile time in an AOT context, right? But other things that rely upon ambient state, that's going to be a little bit more tricky, isn't it, right? Let's suppose you're testing the presence of some context in a cloud platform, and you've got the at conditional on cloud platform annotation that activates a bean exclusively when it's running in a particular cloud platform like Kubernetes or Cloud Foundry or Heroku. That's not going to work here, right? Unless you can trick your application by using, for example, the Spring main cloud platform property into thinking it's running on that platform during compilation. Just bear that in mind. Ambient state that can only be usefully determined at runtime should not be used for at conditional annotations in your AOT world. Which is why, by the way, you shouldn't I love GraalVM, but one thing that can be a real kick in the pants are the wait times. I get why it's happening. It's not hard to understand. GraalVM does a lot of work, and doing a full analysis of our code and all that stuff on the class path can take time and memory. It's no wonder that it takes as much of either as it does, and it has already improved dramatically, even since I first started using GraalVM in earnest less than 3 years ago. It's a marvelous piece of software, but those compile times are hideous. They interrupt my sense of flow, and it's almost a curse that they've improved so much as they have, because the compile times are now fast enough that you don't have time to go pour a cup of coffee or eat some yogurt or do a crossword puzzle, but they're slow enough that you feel like you're being interrupted, that you're being kicked out of the zone. This reminds me of that classic XKCD cartoon, where it's explained that the number one programmer excuse for legitimately slacking off is, "My code's compiling."
which I suspect has more to do with C and C++ and large builds like that. Java and Go and other modern languages have mercifully quick compile times these days. In this one sense, it feels like GraalVM has taken us a step backwards. If I kick off a compile, my mind starts to wander. I've been doing so many of these now that I'm starting to hear elevator music when I do a compilation. So I was thinking I would like it if everybody could hear elevator music. And so I asked. It doesn't hurt to ask people. So I went to the official GraalVM project and I filed an issue. I was excited to see that people responded with support and enthusiasm, and one person even suggested some elevator music. Somebody else responded that it might be useful to have beeps too, which would be nice as well. And then I was very happy to see that Fabio Niephaus, a researcher on the GraalVM team at Oracle Labs, and a doctor, a PhD, along with my favorite other doctors, Doctors Who, Strange, Pollock, Sire, and Subramaniam, responded with a very promising prototype, a --Josh-long-mode that would not only play some elevator music, but also print out this ASCII artwork that says music brought to you by Josh Long, and there would be an ASCII encoding of yours truly. He said, I regret to inform you, that he doesn't think that the PR will be accepted, perhaps because of the copyrighted music. I'm sad. I would love to see that PR get accepted. But he did promise that they're also working on fixing the core problem here, which is the compile time itself, rather than just the symptom, which is the wait. And so that's promising. I think we'll get a fix one way or another.
Working on a bean-by-bean basis is very powerful. If you want to work with actual live-fired beans, however, you can use Spring's bean post-processor. This interface puts you in a position to transform actual objects, not just bean definitions, before they're finally live and handling requests. This is great for infrastructure code, such as frameworks where you need to note or retain or reserve or observe instances and references to instances of objects of a given shape. And when I say shape, I mean anything really, objects that have a certain marker interface or objects that have a certain annotation or whatever you want really, and whatever you could decide given reflection. I want to implement a proxy, for example, using Spring's proxy factory, which makes it trivial to use the proxy design pattern. A proxy, in its most general form, is a class functioning as an interface to something else. So for example, Spring uses it to handle things like declarative transaction management, auditing, security, logging, concurrency, and so much more. There's a great way to decorate an existing object with cross-cutting concerns, like starting and committing a transaction before and after a method invocation. Spring uses these all the time for things like @transactional, @scheduled, @async, and @authorized, and countless others. There are two types of proxies in the Spring world: JDK proxies and cglib proxies. There are two types of proxies in the Spring world: cglib and JDK proxies. JDK proxies are built using the invocation handler API. It makes it trivial to create an object that implements an interface type of your choice and then forwards the actual request to a concrete instance of that interface. In this case, the word interface used in this description above is quite literally a Java interface type. But what if the surface area, the interface of your class, isn't a Java interface, but just some sort of API signature that you expect everybody to observe? What if it's a concrete class for which it makes little sense to extract out a separate Java interface? JDK proxies require an interface, and they were only supported in Spring after 1.1. I can't be sure, but I suspect this is one of the reasons why so much of the early literature suggests using interfaces with Spring beans, and why you'd see things like foo service and default foo service, or foo service and foo service impl, or whatever. Nowadays, that's a bit of an anti-pattern and highly discouraged unless you actually plan to have more than one interesting implementation of that interface, in this case, foo service. That is, suppose you're implementing an interface for an online marketplace, and you might have more than one version of the interface for iOS and Android, as we saw earlier in the qualifier demonstration. Avoid the knee-jerk reaction to create an interface for an object that has the same shape as the object. It only complicates things. Spring supports concrete proxies 2 using cglib, which is a third-party library that's used to dynamically generate bytecode, and in this case, bytecode to subclass an existing type at startup time. The constraint, thus, is that the type be subclassable. So obviously you have to be aware of things like final and sealed. Spring's concrete proxies are unique to Spring. You're using them every time you use a configuration class. They're everywhere. Naturally, creating a dynamic subclass of a given type, registering it in the class loader, and then swapping out your interface for the instance that delegates to yours implies a lot of funny business that we'll need to account for at compile time in the AOT context. Mercifully, Spring can do a lot of this for you. So let's take a look at an example.
Let's look at how we can create a proxy using a bean post processor and have it just work with Spring AOT support. We'll create a new package here called bpp.proxies. Okay, I'm going to create a proxies configuration class. And before we get into the AOT stuff, let's just consider the use case. Okay, so order service, whatever, void increment, whatever, add to price, something like that, double amount, right? And we're just gonna, adding amount, okay? Just a very lazy piece of code here, and it's a service. And let's suppose I want now to have some behavior where whenever somebody calls a method on this, let's create a bean that actually uses that, right? Application listener, application ready event. It'll be called order, logged listener. Whenever somebody uses our object, we're going to have some code that gets run before and after each method invocation. Okay, so here's the order service, and we'll just say service dot add to price, and we'll just call it 7. Okay, good. So there's our invocation. We're not, it's nothing fancy. We're just invoking a method there. Now, in order to make this work, in order to add some behavior before and after, to have a precondition and post condition kind of thing, we need to create, we need to intervene. We need to intercept that method invocation. And one way to do this is to create a proxy. So let's first create the annotation that will demark where we want the proxy to be applied. Okay, so let's look at the, let me just say add qualifier. Okay, we don't need qualifier. I'm just using this for a template for the code. I hate writing annotations, it's too boring. Okay, get rid of that. And we don't really need, we want this to be called logged, I suppose. And we don't really need all these other ones. We just want for the type. So good. So there, I've got my custom annotation. This isn't a Spring annotation. I could, I can create meta annotations for lots of different use cases, but there are no Spring annotations on this one. This is all Java lang, so Spring doesn't know about it. It doesn't care about it. Okay, good. So I want now to annotate this bean with that, and whenever it's involved, whenever Spring compiles the application or when it runs the application, it's going to find. I'm going to create some code to find this annotation, and then to override the definition of this bean, to wrap it in effect, to create a dynamic subclass of it, and insert my logic before and after each one of these methods gets called. Okay, and the way you do that is you create a post processor, a bean post processor, and this, the contract here is pretty simple. You have two callbacks that you can choose to implement. One is called before the Spring bean. One is called before the Spring bean has had its after properties set and add post construct, initialization methods honored, right? That's the before initialization. The second one is after initialization, okay? And that's the one we're going to use, right? We want the fully formed bean because we don't want to have to wait for any other side effects or anything like that. So we've got a bean post processor. We've registered it here, and we want to make some code to, instead of taking this bean, if this bean is a type of, if this bean has our annotation on it, then we want to create a proxy that does what we want. Otherwise, we return the bean, right? So, our default implementation, if we look at the super version of this, all it does is it returns bean. So we could just do that, right? That would be the default version. But what if this class is something that we decide we want to act on? So private boolean matches class name, right? and we can say, okay, if bean class is not null and class name dot get annotation logged dot class does not equal null, right? So if it's not null and the class is not null and the annotation is not null, then yeah, this is a bean we want to be interested in. We need to look at, okay? Okay, great. So we've got that. Now, the thing is, we're just returning a regular old object given an object, and we're going to create a proxy. So the proxy is actually going to have extra signatures, extra types in its signature that aren't compatible with this one, right? It's going to be extra types that we might need to do reflection on, and so on. So we need Spring to know about that, and in particular, we need Spring AOT to know about that. So we could implement this for a lot of use cases, but for this particular use case, the one where we're creating a proxy instead of just some side effect where we note things or something, instead we're going to use a subclass called a smart instantiation aware bean postprocessor. And here it behooves us to override a particular method called determine bean type. Our job then is, given the bean class and the bean name, to determine the target bean class name, okay? So the same rules apply. We can see that this just returns the bean class, so we'll just do that for ours, our first one, unless this matches, okay? So bean class, if it matches, then we need to return the concrete proxied class of the type. Okay, so good. So we need to do that for both, right? So if matches bean.getClass, then do something. Otherwise, just return the bean. Same basic approach here. Now, in order to get the concrete class here, remember this gets called before we actually create the object. So we're giving the framework a way to kind of look ahead and say, okay, here's the shape of the type that will be created should you create a proxy. But we're not actually creating the proxy at this point. That only happens in the post process after initialization. And in order to create this proxy, we're going to use the Spring Framework proxy factory object. Okay, so this is going to be pretty straightforward. We say private static proxy factory, and we're going to create a proxy factory instance if there is a target object. That is to say, if we actually have a live bean, as we do here, then we pass this in and it'll be not null. Otherwise, no matter what, in either case, we'll have the target class, won't we? So we can do a lot, but not everything with just the target class. So let's do that. So var pf equals new proxy factory, okay? Pf dot set target class is target class. Pf dot add advice, and we're going to come back to this in just a second. Pf dot set interfaces, so target class dot get interfaces. Pf dot set proxy target class, right? So set proxy is true. Okay, good. Oh, no, true. There we go. So we want to now implement this part. We'll come back to it in just a second, and then we say return pf. Yeah. Okay, good. So let's. The only thing that we haven't done, is the target, and that's only because that could be null. So if null does not equal target, then pf dot set target. Okay, target. Good. There's that. Now here's the actual implementation of our around aspect. So we're going to say before. Let's see, var method name equals invocation.get method.get name, and then we'll say system out before method name, and here's after. Okay, and we're going to actually get the result now of the invocation itself. So invocation.get method.invoke on the target object there, which at this point we are sure is not null, right? Because this wouldn't get invoked otherwise. And so on, we're going to invoke the target, and we're going to use the parameters, right? So here's the get arguments. There you go. Good. So we're invoking that, and we're returning the result of the method invocation. So this is like a callback, like an event listener for when somebody actually calls a method on an object, on the proxy that we're creating. And so here, we determine the bean type. We say return create proxy, or proxy factory, I guess. null for the actual concrete one because we don't have that yet. And then we can create the proxy, right? Get the proxy class given the bean class.get class loader. Or in our actual runtime thing, we do have the real thing, don't we? So bean bar bean class equals bean.get class and bean class and bean. Whoops. And yeah, good. So that's basically the same code in both places. The only path that's a little different is the fact that the target might be null or not. But basically that extra callback, that determine bean type, gives Spring enough information about the shape of the object that'll be registered at runtime. Okay, I think we're almost ready to run it. Let's just make sure we look after everything. Did I screw anything up? Let's move this up to a separate variable. That way I can just have one definition. I don't have to worry about repeating it. We're returning the actual object here, so we don't need the proxy class. We need the actual proxy. But otherwise, that looks basically good to me. Let's go ahead and kick it off. Okay, the method has been logged. So before add to prices,
In this example, we're using the cohesive design of Spring's AOT support to transparently create proxies that just work. If we've done our job right and we've written our code correctly to leverage the right Spring interfaces, then you can just trust that Spring will do the right thing for your cglib proxies. Sometimes, however, you need to intervene and explicitly furnish hints for the things that you do at runtime. If you're using JDK proxies, then you can explicitly register hints for that with proxy hints registrar. You might also have stuff that you want to do at runtime that requires upfront compile time processing. Code generation, for example, is a very powerful dimension of Spring's AOT engine. We use it all over the place in Spring Framework 6. Let's take a look at a simple example. This time, we'll revisit the code generation to register a Spring Boot actuator endpoint of type compilation endpoint, which we're just making up for this example. It'll contain useless information captured at compile time, like the time and directory in which the code was compiled. Let's take a look.
We've already seen that the Bean Factory, the various callbacks in the Bean Factory world, give us access to the Bean Factory at the very early stages of the construction of the application context, both at compile time and at runtime. We've also seen how the Bean post processor gives us access to beans basically when they're just about to be put into production, but you can still change the shape of those beans, of those objects in the application context. There's another interface at compile time called Bean Registration AOT Processor, and it can be very useful in the same way as Bean Factory Initialization AOT Processor is useful to act on objects in the application context and change them perhaps with code generation. Let's take a look at that possibility. We're going to create a new thing here called code gen, or just code, why not? And we're going to create a new class here called compilation endpoint configuration. And the use case, far-fetched though it might seem, is I want to capture information about the actual application's compilation. So I'm going to create a Spring Boot actuator endpoint. I need to add the Spring Boot actuator to the class path though, so let's just copy and paste that. Command V, actuator, good, and then just make sure I do Maven reload project, and good. Now, this endpoint, I'm going to register it. It's going to be a Spring Boot actuator endpoint and compilation. And of course, if I want to see this, I need to actually enable it in my properties, don't I? So management endpoint web exposure includes everything and show the help details. We don't need that one. Okay, so there's my compilation endpoint. It's going to have some data in it in a map. Okay, and we're going to enrich that map. We're going to replace this object at compile time, right? So map equals new concurrent hash map. So there'll be a default version of the endpoint that exists at runtime that's empty, right? Obviously. Default runtime version. And we'll have another one that exists at compile time that contains the time when it was compiled and the directory of the code. Yeah. Good. Okay. And I'll say map.putAll, map.of instant instant.toString, or whatever, instant, we'll just leave that there. Directory, very good. Okay, so that'll change that, and then we'll create an endpoint here called read operation, public map of string object compilation. Okay, return map.of compilation, and we'll just have this.map, and we'll have a current time as well, so that we can see the delta. Okay, between the compilation time and the current time. Okay, good. So now we've got our endpoint. We need to actually sort of exercise it, don't we? So let's first of all register the endpoint here, the default one, compilation endpoint. Okay, return new, good. And then we're going to create a bean to exercise that. So compilation endpoint listener, compilation endpoint, application listener, and we're going to use endpoint dot compilation var map equals this, and we're just going to log it out, right? So we'll say for var e map dot entry set system out e dot get key equals e to get value, right? Okay, so just a basic example here, but it's going to do something useless at runtime, right? Unless something acts on it at compile time, and this is where a bean registration AOT processor can be pretty useful. Okay, so class compilation endpoint bean registration AOT processor implements bean registration AOT processor. Goody. Okay, so there's this, and we get a callback here, and you can see there's an opportunity here to register a contribution, which is what we're going to want to do. Now we can register this interface just like we did the bean factory initialization AOT processor as a bean method, like this, or we can do put an entry in AOT .factory. So first things first, do we care about this bean, right? If not, if compilation endpoint.class is assignable from registered bean .get bean class, then we care, right? So if it doesn't, then we don't care. We'll just return null. Otherwise, we return a new bean registration AOT contribution. And here, we are going to write some code to post-process at compile time the object that's been, that's going to be passed in at runtime. Okay, we don't have to create a brand new Java Poet session. We can use code, and the first thing we're going to do is get, we're going to get the code and the context. We're going to use that to add a new class, and they call it a feature for an existing component. Okay, so this is basically your chance to contribute a method that gets to post-process the bean that you're contributing, and it's contributed at compile time, so you can do anything you want at that point, right? So var generated classes equals context get generated classes, good, got that, and I want to generate a new one, right? This is ours, so we'll say generated classes dot get or add feature component, and we're just going to call this compilation endpoint dot simple name feature, all right? And we'll use the compilation endpoint.class, and then we have a builder here, and we can use the builder to describe this new class that we're building. We're just going to say builder.add modifier. Modifier is public. All right, not a big deal. Good. So now we have a generated class, and in the generated class, we need to have a method that takes a reference to our compilation endpoint and allows us to either change it or return a new one or whatever, kind of like we would in an actual bean post processor. So here, we're going to create a new method, right? Generated method equals generated class dot get methods dot add post process compilation endpoint, all right? Point. It doesn't have to be named anything in particular. We're just using that. Okay, and we'll get back to that implementation in a second here. But once we have the method reference, right, we can once we have the method, the generated method, we can actually get the method reference and then turn that into a thing that we add to the code. So bean registration code, add instance post processor, method reference. Okay, so that's the basic skeleton of what we're trying to do here. There's an API here, and again, we're gonna be able to use Java Poet here. This is what we just saw a little while ago, but basically, I'm taking the existing body of generated classes and I'm adding another one, right? Very convenient. Okay, now here we need to actually implement this method. So we're gonna have a method that has a pointer to the compilation endpoint, and then we're gonna work on it. Okay, so let's say var output bean variable name output bean. We'll say builder dot add modifiers public modifiers static dot add parameter registered bean, right? So you have to take a pointer to the registered bean, add parameter compilation endpoint, and we can call this input bean, and we'll call this one registered bean. Sure, it doesn't matter, but you can call it whatever you want. These are the names of the parameters. Returned compilation endpoint, of course, because that's what we take in. And then the code looks like this. It's just going to be a code block, right? And we could just provide actual code, right? Just add a statement with Java string and be done with it. Or you can use these builders to programmatically build up your Java code, which is kind of interesting, and I think I'll do that here. I'm only returning one statement. It's just a doozy of a statement, and that statement is $T for type, $L for lexical equals new $T, so type again, parentheses, $T of epoch milli L, okay, and then new Java IO file S, okay. There we go. There's that's the magic code, right? That's all that's doing is, it's going to be a variable of type compilation endpoint on the left. The output variable name is the L, $L. The type of the thing, again, is compilation endpoint. So I'm just duplicating that here because it's compilation endpoint output bean equals new compilation endpoint, right? That makes sense. And then the type on the left is an instant. So I'll say instant.class. And I can actually do that again where I do the Java IO file. I should just do that. It doesn't matter. Okay, anyway, instant, and then system current time milli. So I'm capturing this. This is running at compile time. I'm evaluating the current time, and I'm reifying it as a string, a lexical string that's going to be passed into the Java code unchanged, right? Okay, good. So system current time milli. And then finally, I've got wherever this code is being compiled, wherever the compilation is happening, I'm going to pass that in as a string. And this $S gives me an ability to take a string generated compile time and pass it in as a string correctly in the Java code. And yeah, going back to this, we can fix this as well. New T, right? And it'll just be file.class. Okay, so we're adding that statement, and we're going to say add statement return L, and that's the output variable name, right? Because we're saying that the variable name is equal to output bean variable name, and now we're returning the same thing. And then we want to call build, which is what we've already got done there. So good. So there's our whole method body. Okay, that looks to be correct to me. Let's go ahead and compile the code and see what happens.
All right, the application is started up. There we go. So there's the compilation information. And it was compiled in users JLong download AOT, and the time was 34 minutes after midnight, well, which is wrong. Obviously, it's the wrong time zone, but 34 minutes after midnight. But if you look at the current time right now, it's 35 minutes, right? So it has clearly worked, right? We've captured the compile time state, and we've reified it. We've kept it in the generated Java code, and you can see that here in, guess what, the generated Java code. Let's go down here and check it out. Okay, so bean post processor code, right? AOP application. Where's our? Oh, here, sources. That's got to be more correct. All right, so where's our custom processor? Oh, here's the endpoint feature. There you go. So post-process compilation endpoint, that's our bean definition. And here you can see it says compilation endpoint output bean equals new compilation endpoint instant of epoch milli, capturing that. And here's the code, the actual, it's capturing also the file system path, right? Where the code was compiled. And it got baked into the Java class, which then got registered, right? This is called compilation endpoint feature. Look for that in here. You can see we're saying create the instance and then post-process it, using that method that we have, the static method. How cool is that, huh? You got a way to reify, to change the code dynamically. And testing is very important to the Spring Boot developer experience. Obviously, there are going to be some inconsistencies between the way an application, any application, runs in Java on the JRE versus Java in a GraalVM native image context. And so, to that end, we've made our testing support as solid as possible to help you. Obviously, the basic stuff works. So, for example, if I went to I wanted to test my business logic, right? You remember earlier we created this repository. Let's create a new test for it. Spring Boot test, at test void persist, this kind of stuff. You've got a million of these, I'm sure. And we just inject it into the constructor at autowired. And I just want to make sure that if I call repository.save for a new customer, that the ID is not null. So name, okay, var saved. There's that. And I want to just say assertions, assert not null saved dot ID, right? And also I want to say that I want to make sure the ID, the object itself is not null. So that'll work. That should work just fine. Obviously, I don't want the whole, I want to say Spring application type is none, right? Okay. Good. That'll work just fine. There's our business logic test. Let's just compile it and run it and see. Okay. Now, we can test our applications in the normal way. Maven clean package will invoke the tests on the JRE. But if we want to compile our code and run it in a native image context, then we can activate the native test Maven profile in the same way that we can also access the native profile to get a native binary for the production code. Okay. Now we're just going to run this. If you go to the target directory, you'll see a native tests binary that was compiled and contains the results of our tests. So there's the test report, 2 containers found, 1 test found, 1 test started, 1 test successful, obviously, and so on. The customer repository test persist is successful. So that's cool, right? Now you have the ability to actually do your business logic and make sure that that works. And by the way, when you're running these tests, you can also run that Java agent and capture information. I mean, you can do all sorts of things with tests to help make your application movement, the migration to native, all that much easier. Now, let's say you've written some hints, a runtime registrar, hints registrar, and you want to confirm that it's working as expected. Well, earlier we looked at an example where we had a runtime hints registrar where we created hints for a CSV file. Well, I want to test this. Okay, so I want to test that. So I'm going to create a new test.
And in it, I'll say, okay, I'm going to create var hints equals new runtime hints. And I'll create a reference to the registrar, so that'll be new migration dot hints registrar, okay? And I'm going to get a pointer to the class loader, which is get class dot get class loader. We'll say registrar dot register hints, okay, with the class loader. Okay, so we've registered the hints. Now we're going to say assertions that, and we're going to use some predicates. We'll say runtime hints predicates dot resources for resource data.csv except the hints that we've given. Okay. Good. Let's go ahead and run this and see what we get. Very good. So it seems like we did actually successfully register that hint. Let's try the negative. Let's prove a case that shouldn't work. And yes, it fails. Good. So hopefully you can see that you have not just your normal means of testing to ensure parity across one environment or another, but you also have code dedicated to making it easy to test the components that you have to register specifically to make native work.
We've come a long way. When I started covering Spring Native in 2020, a build took 10 minutes and only worked for the smallest number of specific scenarios. Now, here we are in 2022, and I can all but effortlessly get a Spring app working in a GraalVM native image context in less than a minute. The performance and memory usage implications are hard to ignore and very persuasive in a context where you have to pay by the use. And I think the inertia required to make the move to AOT will become easier and easier to overcome in the next days, weeks, months, and years as the community embraces Spring's newfound AOT support. I hope that this video makes it easier for everyone. Right? I want everyone, application and framework developers alike, to leverage this new mechanism to improve their offerings, to improve their application's production prospects and efficiency. Just look for pointers to types like runtime hints registrar, bean registration AOT processor, and bean factory initialization AOT processor in the Spring Boot codebase for guidance. And these don't even begin to cover the implementations provided by the projects themselves, like Spring Security, Spring Data, Spring Cloud, Spring Shell, Spring Integration, Spring Batch, etc. We've only just begun to scratch the surface here, and I can't wait to see what comes of this. Now, bear in mind, these things may change in relatively minor ways in the coming weeks and months leading to Spring Boot 3 later this year. But conceptually, what you've seen here is the future, and it's here for you to try out today. We'd love to hear from you. Don't hesitate to reach out to us on Twitter or via the Stack Overflow forums or the GitHub issues for the respective projects that you care about. We're all working very hard to make this work for you. Let us know.